Hello, and today we're going to talk about Chapter 6C, which goes over the normal distribution. So first of all, what is a normal distribution? The normal distribution is a symmetric bell-shaped distribution with a single peak. Or in other words, it's a unimodal symmetric curve. However, it has some extra conditions in order for it to be a normal distribution. Most data values are clustered near the mean. Data values are spread evenly about the mean. The further away the points are from the mean, the more unlikely or rare they are. And the fourth condition, which probably isn't a very strict condition, but generally these can be created by many factors, including genetic and environmental factors. So a good example of something that is a normal distribution is IQ scores or the weights of adults. Both of those follow a normal distribution. All right, so we have our normal distribution, but what does that really tell us? Well, this tells us that we can actually figure out what percentages lie within a certain distance of the mean. And so by percentages, I'm referring to the percent of our data set. So we have the 68, 95, 99.7 rule for a normal distribution. Oftentimes, this is also called the empirical rule. For the first part of the rule, it says about 68% of the data will fall within one standard deviation of the mean. So that means if we go either left one standard deviation or to the right one standard deviation and completely shade this area, we would expect about 68% of our data points to be between these two numbers. For the second part of the rule, it says about 95% fall within two standard deviations. So if I'm looking between these 2 points, and I was to look at all the data points that lie within this region, we would say there's about 95% of those. Then, of course, I can go one further out and say that between this number and this number, we would expect about 95 or 99.7 of the data set is going to lie in that area. Now, of course, what might be helpful is to actually break this up into separate sections. What I want to do is I want to look at what the area is of each of these sections. So I know that if I go between this line and this line, we have about 68% of our data. So everything between here is about 68% of our data. Now, what if I just want half of that? Well, that would give me the area of 34%. Because again, 34 plus 34% is 68%. Now, what about trying to find these two sections? Well, again, we know that from here to here and everything shaded in between, that's 95%. And we know the middlemost is 68. So if we take 95 minus 68, that should give us about 27%. So that's what's left in both of these regions here. However, we want half of that to get each section. To take 27 divided by 2, and we're left with 13.5%. Now, what's left in these little regions here? Well, again, we know that if I went from this point to this point, that's 3 standard deviations out, so that was 99.7%. We take that minus the area 2 standard deviations away from the mean, that's 95%. Subtract those, and we end up with 4.7%. And of course, if we divide that by 2, we're left with 2.35% in each of those. Now, if you do try and add all 6 of those percentages, you'll notice that we're still missing a little bit of the percentage from getting 100. That's because it's really hard to tell, but there is a little region here and here at the very tips of each tail. And in fact, we're actually missing, we take 100 minus 99.7%, we're actually left with 0.3% remaining. So of course, if we take that divided by 2, we end up with 0.15%. Now that's a pretty small area, but that is what's remaining in each tail. So if we're trying to figure out what percentage of our data is in each of these sections, this is basically what we have according to this rule. Now, this rule is more of an estimate, but it's a pretty good estimate compared to the actual values. So in this example, we have test scores that are normally distributed. Again, that is very important. And they have a mean of 100 and a standard deviation of 20. So what I like to do first before I go through any of these problems is I like to draw out the normal distribution curve. So I know that if I go 1, 2, 3 standard deviations out, so if I go 3 standard deviations out, this third line away from the mean should be where the curve almost touches the number line. Now again, we're going by a distance of 1 standard deviation for each tick mark. 1 standard deviation is 20. So if we were to take 100 plus 20, that would give us 120. So in other words, every time we go 1 tick mark to the right, we're just adding 20 to the previous number. So we have 120, we have 140, and then 160. And then same thing going to the left, except we actually subtract. So 100 minus 20 is 80, then 60, and then 40. So for this first problem, we want to find the area or percentage between 60 and 140. In this case, we just want to find this shaded region. So notice that both numbers are in fact 2 standard deviations from the mean. So that tells us that according to the 68, 95, 99.7 rule, that the percentage of values between those two numbers is 95%. For the second problem, we want the percentage of values that are less than 100. Well, 100 is right in the middle, and essentially we were trying to find the percent to the left of it. So what percentage is shaded? Well, there's only about 50% that is shaded, and then the other 50% is not shaded. Now, what about if we're looking at less than 120? Well, this one's maybe a little bit trickier because, of course, we know that the area shaded to the left of 100 is 50%, but we're adding a little bit more to it. In fact, we're adding this little section here onto the previous answer. So we know that this is 50%, but what is this section? Well, from the previous slide, we found out what that area is. And we know that 120 is 1 standard deviation from the mean, but we're only looking at half of that area. So what I'm talking about, we know that we have this area, which is 68%, but we're only interested in the right half of that region. So we only wanted half of 68, which is 34%. So 34 plus 50% is 84%. For the last problem, it says greater than 60%. Now there's a couple ways we can actually find this one. We know that 60 is 2 standard deviations to the left of 100. So that tells me we may need to use the 95% area. So we know that this part is in fact 95%. So sure, we have that area, which is nice, but we still need to find the area of this tail. Well, if the middle area is 95%, then what's left over is 5%, which has to be split up into the two tails. So this is 2.5%. So that means that this tail must be 2.5%. Adding 95 plus 2.5 will give us 97.5%. It definitely helps, especially if you're a visual learner, to draw the curves out and shade the areas. So in the previous slide, I was talking about a number being 1 or 2 standard deviations from the mean, but we can kind of get a better idea of how many standard deviations a number is from the mean if we calculate its standard score, or what I'm going to end up referring to it as the z-score. The z-score essentially is how many standard deviations a number is from the mean, and if it's negative, then that tells me that it is to the left of the mean. If the z-score is positive, it is just to the right of the mean. And of course, if the z-score is 0, then the data value is actually in fact the mean. So in this example, we're looking at a psychology exam, and they were normally distributed with a mean of 67 and a standard deviation of 8. And we want to find the standard score for an exam score of 55. So what I'm going to do is I'm going to take 55 minus 67, and I'm going to take that and divide it by 8. Now, on your calculator, it is important to make sure that you put the numerator in parentheses, since we need to make sure we do the subtraction first before the division. So the z-score we should get is negative 1.5. So this z-score tells me that 55 is 1.5 standard deviations to the left of the mean. So now what is the standard score for an exam score of 85? Well, we do the exact same thing. We just plug in 85 into the formula, make sure we do the subtraction first, and we end up with a z-score of 2.625. For the last one, it says about what percentage of exam scores were below 83. Well, we can at least calculate the z-score first before we fully answer this. We're going to take 83 minus 67 and divide it by 8. And we end up with a z-score of 2. Now, the only thing that really told us anything about percentages was the 68, 95, 99.7 rule. And because this is exactly 2, that means it is 2 standard deviations. So if I draw that curve out again, if the mean was 67, this is 2 standard deviations to the right, we have 83. Again, we know that between 83 and this other number that's 2 standard deviations to the left is about 95%. And I think we did this problem, a similar problem on the last slide that said that the area of each tail was 2.5%. So if we add those together, we end up with 97.5% of the values are less than 83. So in other words, this exam score of 83 is actually really good compared to the rest of the class, as they made it in the top 2.5% of the class. This brings us into what we call percentiles. The percentile of a data value is the percentage of all data values in a data set that are less than or equal to it. So oftentimes you'll hear of percentiles when you're looking at exam scores, whether it is the SAT or the ACT or some other nationwide or even statewide exams. So for example, you'll have P with a subscript of 23. This is equal to the 23rd percentile. And what this means is that there's about 23% of the values are less than or equal to that percentile. So if we're talking about exams, we would say that there's about 23% of all exams are less than itself. Now, it's not necessarily saying that the exam score is 23%, but rather, whatever the exam score is, only about 23% of other test takers had a score less than the score that you had if you were in the 23rd percentile. Now, what's also nice is that this is for a normal distribution. Assuming that we have either the z-score or the percentile, we can figure out the other value. And in fact, in that last example, we had a z-score of 2. And notice that that does give us a percentage of 97.72, which is pretty close to what we estimated it to be. Now, one warning is that you only can use this if this is for a normal distribution. If you do not have a normal distribution, meaning that your data set has some other shape to it, you will need to find some other method for calculating the percentile. So just to get ourselves familiar with the table, we're going to find the standard score for the following data values. So the first one is we have a data value in the 20th percentile. Now, I actually do have a separate handout, which I did include in my math lab. And in this, it actually has a table with all of the z-scores from negative 3.5 down to positive 3.5. In this case, we want to find the 20th percentile. So we need to look for the number closest to 20. And in this case, it's between these two numbers, 19.77 and 21.19. In this case, 19.77 is closer to 20. So the z-score that corresponds to that is negative 0.85. If we do this for the 80th percentile, we just again look to see what number is closest to 80. In which case we have 80.23, and that gives us the z-score of 0.85. Notice that these two answers are just the positive and negatives of each other. And this is just due to the symmetry of if I was to draw this out, and I had 20% in this left tail, well, the remainder must be 80%. So this was negative 0.85. If I was to flip this around, notice that I basically end up with 80% in the left tail and then 20% in the right tail, and this is just positive 0.85. And again, this works because of the symmetry in the normal distribution. Last one, it says to find the 63rd percentile and to find the z-score corresponding to that. In this case, we had a z-score of 0.35. So the last part says that we're looking at the body mass index, and these are normally distributed with a mean of 26.2 and a standard deviation of 4.7. So first we're going to find the standard score, or z-score, for the body mass index of 24.5. So z is equal to 24.5 minus the mean, which is 26.2, divide that by 4.7. Our z-score is negative 0.36. Now in this case, the closest answer that we have to negative 0.36 is negative 0.35, and that gives us the percentile of 36.32. So this basically means that this person's body mass index ends up being in the bottom 36% of all body mass indexes. For the last part, what BMI corresponds to the 40th percentile? Okay. So again, we just kind of look to see which of these has the number closest to 40, and this corresponds to a z-score of negative 0.25. Now notice that this is not the body mass index. This is just the z-score corresponding to it. So how do we find the body mass index that corresponds to this z-score? Well, recall, what we basically have is we just have everything except for the data value. So if I plug all the numbers that I have into the standard score formula, we basically can just replace our data value with x and plug in the numbers that we do know. And from here, we can go ahead and just solve for x. So basically, I just need to multiply 4.7 on both sides. So we have negative 1.175 equals x minus 26.2. And then from here, we just add 26.2 to both sides. So here we have our BMI of 25.025. Well, thank you for watching, and I'll see you in the next video.